Okay guys, this is bond enthalpy. This is a really tough subject, and I'm assuming when I do this, you've got a basic understanding of enthalpy diagrams. If you haven't, you might find this a little bit difficult, and it's probably best to learn that better before you watch this video. Okay? So what I've done is I've set up an enthalpy diagram, enthalpy of one side, and progress of reaction, which basically means time on your x-axis. And let's say, for example, my reactants start off with, in fact, let's put it here, this much energy. So here's my reactants. And my products end up with this much energy. My products are lower in energy than my reactants, obviously, because the band's lower. That means they've lost energy. Energy has been given out to the surroundings. So that's an exothermic reaction, and it will increase the temperature of the surroundings. But this diagram is a bit misleading. What happens is it doesn't go straight from reactants to products. They don't just magically change. What we have to do is a little bit more complicated. So I'm going to use an example equation. Let's say we've got CH4 plus 2O2, and we're going to change that into CO2 and 2H2O. Okay? Now, these don't magically disappear and these reappear. What actually happens is the bonds in these are broken, and then new bonds reform to make these up. So there's two steps to our reaction. First of all, we need to break all these bonds. So I'm just going to draw my molecules out to make it a bit easier to see all my bonds. So with CH4 and O2, it might seem easy, but in your exam you could get a much more complicated molecule. So it really helps to draw all the bonds out, otherwise you'll just get confused. So here's my CH4, here's my 2O2s, here's my CO2 and my 2H2Os. Okay, here's what actually happens. First of all, we need to break our bonds before we can make the new ones. Carbon can only make 4 bonds. So before it can make a bond with the oxygen, it first has to get rid of a hydrogen, or 2 hydrogens, so it can make a double bond. Okay? In reality, in most equations, you're not going to need to break every bond. But we can assume, just to make things a lot simpler, that every bond gets broken. That way we don't have to figure out which ones do and which ones don't, which sometimes is impossible to know. So we just assume they're all broken. Now, a rule is, when bonds are broken, they take in energy. Imagine my 2 hands are 2 atoms and my finger's the bond. In order for this bond to be broken, my atoms need to shake around enough to snap it and basically snap it apart. Okay? So essentially my atoms need to move around faster, vibrate more. And to do that, they need more energy, so they take in energy. So, breaking bonds takes in energy. On my enthalpy diagram here then, as I break the bonds and my reactants take in energy, the enthalpy of my chemicals is going to increase up to a certain point. That's to break the bonds. So if this is CH4 and 2O2 down here, on the top here, I've got all my atoms with no bonds with them whatsoever. What then happens is new bonds are formed. And when new bonds are formed, they give out energy. Okay? So first of all, they take in energy to get to the top to break all the bonds. They'll then give that energy back out so that new bonds can be formed. If we think about the analogy before, if they needed to take in loads of energy to break, in order to come back together, they need to slow down again. So they need to give the energy back out. So as my chemicals are giving the energy back out, the enthalpy they have is going to decrease. So it actually looks a little bit like a parabola or a bell shape, like that. So taking energy in, giving energy out. Okay? This top line here, in fact I do it there, the difference between your reactants and the top line, this is called the activation energy. And this is the energy needed to start the reaction off. If I don't have this much energy to start off with, I can't break all my bonds. And if I can't break my bonds, I can't make new bonds, so the reaction can't happen. Okay? And there's a calculation we need to know. Okay, I'll just redraw the same one up. Here's my reactants. And here's my products. So first of all, they need to take in energy in order to break all these bonds. So that's a positive energy change. And what we've done here is we've got a table, and you'll be given this in the exam, you don't have to learn these numbers, of the type of bonds and their bond enthalpy. Bond enthalpy is how much energy it takes to break a bond. Notice it's all positive because they're taking in the energy. So all I do is I add up all the different bond enthalpies in my reactants. So I've got a carbon H bond, which is 413, and I've got that 4 times. I've also got O2 bond, so 497, and I've got that 2 times. So if I add all that up, I'll get an answer. I haven't actually got a calculator on me. Let's just say it comes to 2,600-ish. That is how much energy it takes to break all my bonds. So that's what they suck up. When I make the new bonds, they're going to give energy back out. Okay? Now, the amount of energy a bond gives out when it forms is exactly the same as what it takes in when it breaks. So I can use these same numbers. All I need to do is make this positive into a negative. So I've calculated all my bonds broken. I need to subtract from that all my bonds which are made. So I've got a carbon to oxygen double bond, which is not on here. Let's say it's 500. I'm just making that up. So we've got 500, and there's 2 of them, so we're going to times it by 2. There's an OH bond. OH is here, so that's 463. And we've got that 4 times, so let's times that by 4. So that'll come to roughly 2,800-ish. So what I'm going to do is I'm going to get the energy I gained when I broke my bonds, and I'm going to subtract the energy I lost when my bonds formed. 2,600 minus 2,800 will give me minus 200. And if you flick back the video to the start of this video, you'll see my reactants were higher up than my products. So my products had lost energy, they'd lost enthalpy, which is why it's a negative sign. And if you're stuck for the units to this, look at the table. Mine doesn't have one, but in an exam, they'll always have the units in the table. And I've never not seen it be kilojoules per mole, so kJ mole minus 1. And that is bond enthalpy.